Okay, so today we're going to learn our shortcut. Um, and so we're going to first consider the function f of x equals 3. That's a constant function, a horizontal line. You can think of it as y equals 3 as well. So if we're talking about the slope of the tangent line, remember when the function is just the line itself, derivative means rate of change of the graph at any point. Well, if it's a line, it's got constant change everywhere, so the derivative is always the same everywhere. So in this case, it's a horizontal line. We know the slope of this line is 0. So the derivative at any x value is 0. Or if I said, like, I want to draw the tangent line at any point, the tangent line is the line itself, and the slope of that line is always 0. So for a constant function, the slope of any, I'll call it a tangent line, even though it's really just the line itself, is always 0. So based off of thinking about it graphically, we could say that if f of x, if our function is just a constant, we can say the derivative of that constant is always going to be 0. So that's a rule that we can remember. Now, we're going to look at how we can do the derivative, the shortcut rule. This is our first shortcut rule, by the way. Right? If f of x is a number, then its derivative is 0. If we think of our shortcut rules down here, we can apply them to any, we'll call them polynomial type functions. We'll talk about what that means a little bit later. So the derivative, I'm just going to do some, and let's talk about the rule afterwards. It's called power rule. This one is 6x minus 2. This derivative, we don't have to do that whole limit process. This is the shortcut. Negative 15x squared plus 4x minus 3. This one, we're going to actually talk about what rule I'm doing here. So the first thing is, I have 3 terms, and I can do the derivative of each term independently of the other. Remember, the definition of a derivative is based in limits. So if I'm trying to find the limit of a polynomial by the properties of limits, I can just do the limit of each one independently. So I can do the derivative rule or power rule for each term. So if I think of just 6, that's a constant, so its derivative is 0. The next thing I do is, if it's not a constant, how do I take the derivative of this guy? Well, the derivative of x to any power, and the constant, negative 3, by the way, comes along for the ride. Now, the derivative is going to be 3x squared, because the rule is, let me erase some of this stuff over here. The shortcut says you take the power of x, you put it in front, so that's what I did right here, and then you recopy the base, and then you reduce the power by 1, so that's where the 2 comes from. Okay, now, because it's based in limits, right, the definition of a derivative is based in limits, basically when I want to take the derivative of 3x squared, negative 3x squared, I can deal with the negative 3 later. I can take it out just like when I do a limit, then just do the derivative and then multiply it by the answer later. I do the same thing with constants in limits as well. Okay, so if I apply that power rule again to the last term, I can pull this out of the differentiation process, my constant. Then I can think of x to the 4th. The 4 comes down, I recopy the x, I reduce the power by 1. So then f prime of x becomes negative 9x squared plus 24x cubed. So if we look back at the other ones, that's what I was doing. Now, I don't really need to pull the constant out, because all I end up doing later is taking that constant and multiplying it by the former power, right? The power was 3, I pulled it down. I take that constant I pulled out and I end up multiplying it by the power when I move it down. So we're just going to do that in one step. So if I take the power and I bring it down and I multiply it by the constant, I get my negative 15. I recopy the base x, and then I reduce the power by 1. If I do this on the next term, the 2 comes down, the power comes down and multiplies by the coefficient that's there. That's how I get the plus 4. I recopy the x. I reduce the power by 1. 2 minus 1 is 1. And I don't need to show that power of 1. On this guy, this is a power of 1. So if I bring it down and multiply it by the constant that's out front, I get negative 3. I recopy the base, and then I reduce the power by 1, which is x to the 0. Now, anything to the 0 power is equal to 1. So then if I do negative 3 times 1, I don't need to show this part. Then, this is just a constant, and the derivative of a constant is plus 0. So I don't need to show that. If we look at this guy, the 2 comes down and multiplies by the 3. So I get my 6. I recopy the x. I reduce 1 off the power. I get x to the first. Same thing happens here. If this is x to the first, I multiply by my negative 2. And then I go x to the 0 because I reduce that by 1. And then the constant, 3, its derivative is just 0. And I don't have to show plus 0. So another rule to note, we already have this rule that the derivative constant is 0. Now if we look at a linear term, okay, remember, this term is not a linear term because it's squared. This term is a linear term. What kind of graph does negative 2x make? If I just look at that term by itself, it's a line, and so therefore its derivative will be the slope of the line at any point on that line. Well, if it's a line has a constant slope. So whenever we have x to the first, the derivative is just going to be the coefficient. So you could notice that I don't really have to apply a power rule there. It's something we're going to memorize. Just like I didn't need to apply power rule here. We know that the derivative of 3 is plus 0. Notice here when I have my linear term, the derivative ends up being just minus 3, just whatever the slope of that line would have been, and so on and so forth. All right, let's look at this. How do we deal with negative exponents? Does power rule still apply? It does. The negative 1 comes down and multiplies by the coefficient. So it's a 2. I recopy the x. I reduce the power by 1, so it becomes a negative 2. The power comes down on the next guy, multiplies by the 3. I get a negative 6. I recopy the x. I subtract the power by 1. And there is my derivative there. Now, we don't like negative exponents in our answer, so we're going to deal with this issue a little later, the simplification. Can I apply power rule when my powers are fractions? You can. The 2/3 comes down and multiplies by 6. So 3 goes into 6 twice. That ends up being a 4 when I multiply 6 times 2/3. Here's how I think about subtracting 1. I think of subtracting 3/3. If it's a fraction, I make the denominators the same. 2 minus 3 is negative 1/3. The negative 2 comes down, multiplies by the 4. I get a negative 8. X to the, I subtract 1. I get negative 3. Again, I don't like negative exponents, but we're going to deal with that a little later. Okay, so the negative 1/2 comes down and multiplies by negative 6. So I know 6 times 1/2, that goes into 6 3 times. That's going to be 3. And because it's a negative times a negative, it's a positive 3x. I'm going to subtract 1 off of that power. I get negative 3/2. Here the 1/2 comes down and multiplies by the 3. I get 3/2. X to the, if I subtract 1 off it, I get negative 1/2. Once again, I don't love those negative powers. We're going to deal with those a little later. So based on what we talked about here, we're going to make a rule. d dx of x to the n is going to be n times x to the n minus 1. This is our power rule. A couple of things here. This d dx, d over dx, we're back to our Leibniz notation here. We talked about Leibniz versus Newton, and Leibniz notation is nice here. When you have a d over a dx, it's a verb. Okay? And it says, take the derivative of whatever's inside the parentheses. All right, so it's saying take the derivative of x to the n. So I could say something like take the derivative of x to the 4th, and that would be 4x cubed. All right, so let's look at some examples now that aren't set up nice in polynomial type functions. And we'll see what that means. So when we say polynomial form refers, what it means is we got to have a bunch of terms, and we have to have, like, x can't be in the denominator, and x can't be in a root, a square root, a cube root, whatever. So we want to change all x's and denominators to negative powers, right? We know with our algebra rules that will turn into a negative power or negative exponent, and this will turn into a fractional exponent or fractional power. Whoops. So if we look up above, they were already in that form for us. I had some that were in fractions. Those would have came from a root. I had some that had powers that were negative. That would have been an x in the denominator. So let's look at when they're not posed like that. We first have to do a rewrite of f. So I can bring this up to the numerator because it has to be in our form for power rule where we've got x to a power. And if it has a number in front, that's fine. Like this case, it has a 2 in front. So this one now is ready to go. So I'm going to use, well, okay, we'll stay with this. F prime of x, we apply our power rule. We get negative 4x to the negative 3. And then minus 12x squared. That's our derivative. We do not like negative exponents. So we'll typically write this as a positive exponent by bringing it back down below. And then we typically even like to get it in one fraction if there's multiple fractions. So it'll be negative 4 minus 12x to the 5th over x to the 3rd. I did some common denominator work there. I'm not showing you every step. We can talk about that in class when you start doing some of the practice. You'll have a bunch of these in practice. Okay, how do we simplify this thing? First, we want to do a rewrite because, again, we can't have the x in the denominator. So we rewrite it. There's a couple ways you could think about this. I like doing this. I can decompose that addition of fractions like we've done before, and then simplify each term. And now I can do the derivative fairly easily with power rule. Remember, for power rule, the 3 comes down, multiplies by the coefficient, so that's 9. I reduce the power by 1. So that's why I get a 2. Remember, this guy is just a linear function, and the derivative is always its coefficient. I drop the x if it's x to the first, and then the derivative of a constant is plus 0, but I don't need to show that. Okay? Sometimes this is not polynomial form, it's factored form. Sometimes I got to multiply it out. So I get x squared plus 2x plus 3x is 5x plus 6 times 2x plus 1. So then I got to multiply again. And I'll get 2x cubed plus 11x squared plus 17x plus 6. Okay, so if you distribute the 2x and combine like terms, distribute the 1 to everything, combine like terms, you're going to get this polynomial. You can pause it and do that on your own if you like. Now I can apply power rule to it. So the 3 comes down and multiplies by the 2. I recopy the x, I reduce the power by 1. I bring the 2 down, multiply by the 11, recopy the x, reduce the power by 1. This guy is just a linear function, so its slope will be my derivative, and this just has a derivative of 0, which I don't need to show. There's no negative exponents in my answers, so that's good. All right, so this guy will be more of the same. I can decompose my addition of fractions. So now when I simplify, I could write it as 1 over x squared, but I don't want the x in the denominator, and 5 over x to the 3rd, right? So then I take another step to write it as x to the negative 2. Whoops. Minus 5x to the negative 3. Now I can do the derivative. So remember, the goal here is to get everything in polynomial type functions. And that means You can't have your x in the denominator, and you can't have your x under a root. Once I do that, this is what I did here. I can then start doing power rule. I want to subtract 1 off that power, so it becomes -3. I got the -3 comes down, I get a 15. I subtract 1 off that power, comes x to the -4th. We do not like negative exponents, so I can put them back down to the bottom so that they are positive exponents. And then I can get common denominators and add. Again, you can pause the video and see if you can get there. That's our derivative there. So this is a shortcut. Trust me, doing these without the shortcut, like by the limit process, would be a nightmare. It would take really long, a really long time. So this shortcut, even though it seems like it's not so short, it is actually helpful. All right, so x can't be under a root. So I have to change my root powers to fractional powers. Remember, the power on the inside is the numerator of my fraction here, and the root power becomes the denominator there. Okay, so now I also can't have x in the denominator, so I can simplify this a little further. I could think of this as 3/3. It's x to the first, right? So this is going to be 3x to the 1/3, because when I divide my x's, I subtract my powers. So that's 3x to the 1/3. Now it's in polynomial form, so I've got to change that thing into this thing, and now I can do my power rule. 1/3 multiplies by 3 to give me 1. I recopy the x. I reduce by 1, so I'm going to subtract 3/3 off that. So I get -2/3. I do not want negative exponents, so it's going to be 1 over x to the 2/3. I also do not want fractional exponents, so you have to turn that back to a root. Remember, the top number in the fraction stays with the x. The bottom number is the index on the root. There's our derivative using the shortcut. All right, this one's already in a good form, so it's going to be about the simplification afterwards. If I do -4 times 3/4, the 4 and the -4 cancel, so I get a -3x. So I brought the 3/4 down and I multiplied by -4. Now I'm going to subtract 1 off it, so I get -1/4. Then I bring the 1/4 down and multiply by the 2, so that gives me a 1/2. And then I reduce by 1, so I get a -3/4. Alright, so I want to get rid of my negative exponents, so this is going to be a -3 over x to the positive 1/4. I just bring it below. I'm going to bring this one below. It's already set up as a fraction, so the 1's on top, the 2's on the bottom, so the x to the 3/4 will go on the bottom with the 2. If you're not sure how to do that, if we take a look on the side, it really means 1/2 times 1 over x to the 3/4 if I want to get rid of that negative exponent. When I multiply these, I get the 1 times the 1, and then I multiply the bottoms to get my bottom. All right, now I need to combine this, and this is still f prime of x. Now I need to combine this using a common denominator. So my common denominator is going to be 2x to the 3/4. So I'm going to get, let's see, I need to multiply that by a 2, so it's a -6. And then x to the 3/4, it's going to be x to the 1/2. Plus this one was already the same, so it's +1. I want to get rid of my fractional exponents. Again, this might be a place where you can ask me in class. All right, if you're like, what the heck, how did you do that common denominator? Totally understandable. I don't want to sit here and explain it. For those of you that do get it, it's a waste of time on the video, or I just don't want to make the video longer than it is. I won't say it's a waste of time, but you guys can ask me in class if you're not getting it, and it's perfectly understandable. It's not easy stuff, so don't be afraid to ask. And if it's all of us that need to see it, I'll do it for everybody. So again, don't be afraid to ask that.